Welcome back, chemists. We are now starting a mini unit on reaction rates and equilibrium, and the focus of this lesson is an introduction to rates of reaction. At the end of this video, you should be able to describe the factors that affect rate of a reaction, explain the concept of reaction rate as it relates to collision theory, be able to examine and identify the parts of an energy diagram, also known as a reaction coordinate diagram, and finally, understand the effect of catalysts and inhibitors on reaction rate. So I thought it would be cool to kind of start this topic by looking at different reactions. So for example, in chemistry lab, you're probably used to reacting magnesium and hydrochloric acid, and you know that starts pretty much very immediate. It's very, very fast, a lot of bubbling going on, a lot of formation of hydrogen gas, even sodium and water, right? As soon as you throw sodium into water, it's kind of like a little mini explosion. Burning a match, combustion of fuel, these are all examples of rates that occur very, very quickly. Your moderate reactions are more like food spoiling, rusting of iron, baking a cake, food digestion, and cooking. And then the really slow reactions, such as forming diamonds, weathering of rocks, settling concrete, and silver tarnishing. If you went on to study chemistry in upper level science courses, you would learn more about some of the driving forces associated with why the rates of reactions are what they are. But for our purposes, I just wanted to show you some different examples of reactions that proceed very slow and very fast. So let's talk about a rate. What is a rate? So a rate is really measuring changes that occur within an interval of time, right? So it has two components, something that, usually we look at change in quantity over change in time. And so that is exactly how we're going to define it in this class. A rate measures changes that occur within an interval of time, and we'll focus on the rate of a reaction being expressed in terms of moles per second, for example. You could also have molarity per second, like for example, if you have a reaction that's occurring in solution. But for our purposes, we're focusing primarily on the disappearance of reactants when we're looking at rate of a reaction. There's a really simple theory to help us understand what occurs on the particle level in order for a reaction to occur. This theory is called collision theory. And so collision theory is very simple to understand. All it says is that atoms, ions, and molecules, when they can react to form products, they have to collide with each other and they have to collide with enough energy. So those two things have to be met in order for this to occur. So if they don't have enough energy, for example, they're going to bounce apart. And bonds holding these molecules together are going to break if they're supplied with enough energy. So that energy component is really, really important. Now, this energy that's needed to break apart molecules actually has a special name. It's called the activation energy, and it has the symbol E sub A. This is the minimum energy colliding particles must have in order to react. And really the purpose of this is so that the particles can collide and break those bonds and form new ones in the products. So during a reaction, there is an in-between state called the activated complex, or sometimes it's also called the transition state, depending on which book you're reading. But this is really what we call an unstable arrangement of atoms at the peak of the activation energy barrier. It exists for a very, very short amount of time, so 10 to the minus 13 seconds. And a way to visualize the progress of a reaction is something that looks like this. So this is called a reaction coordinate diagram, and you can see on the left, on that y-axis, you have energy, and on the x, you've got time. And so when we want to focus on labeling the parts of this reaction coordinate diagram. So first up, let's take a look at our reactants, right? So right there, that is energy of the reactants. Over here, this is energy of your products. So it kind of looks almost like a roller coaster in a way, right? Notice you have to go up and then you come back down. This has a very, very special name. This is kind of what I was referring to earlier. This is called the activation energy. This is the energy needed, again, to break apart those reactant molecules and form those new products. And so that has the symbol EA. and then we say that this is the activation energy of the forward reaction. Usually when we say activation energy, we're usually only talking forward, right? At this point, we haven't talked so much about reactions occurring in the opposite direction, but don't worry, that's coming. The other thing that's important is you see that dotted line I just drew in there? Notice that it goes from the energy of the products down to the energy of the reactants, where they started from. This is a really, really important place, and it's kind of a nice time to talk about this because remember, this is going to be the enthalpy of your reaction. So I don't know if you remember enthalpy, but enthalpy is really the energy that's absorbed or released during the course of a phase change or chemical reaction. You probably learned about this back in your thermochemistry unit. But that change between the reactants and products there, that's called the enthalpy, or the energy that is absorbed or released as a result of the reaction. Now this diagram in particular is technically an endothermic process being illustrated here, and we know that because the products are higher in energy than the reactants, which tells us that more energy has to be absorbed by your reaction in order to make it occur. Now let's talk about some of the factors that affect a rate of a reaction. First of all, we'll talk about temperature, then we'll talk about concentration, and then we'll talk about particle size or surface area. The other thing we'll talk about is the addition of a catalyst. So let's first talk about temperature. Increasing the temperature of a reaction mixture increases the frequency of the collisions, right? So that's a good thing. We want the particles to collide in order to form products. And it also allows the particles to have enough kinetic energy to get up over that energy barrier for the activation energy. So temperature is one of those interesting things that we always try to control because we can allow those products to form more easily with an increase in temperature. Concentration is another one, right? With concentration, if we increase the concentration, this causes an increase in the frequency of collisions. Notice that there's no mention about the energy of collisions, and that's really important. So you want to make note that changes in concentration is not going to change the energy. The only thing that changes the energy is temperature. How about particle size? Well, it's actually similar to concentration in that the smaller the particle size, the larger the surface area for a given mass of particles, right? So basically what I say is that if you have really small powdery material, right, there's more area of it exposed, so we say it has a greater surface area, right? It has a smaller particle size, a greater surface area. And then adding a catalyst lowers the energy barrier of that activated complex, right? So it's going to take that big hump that you saw for that potential energy diagram and make it a little lower. It provides a new reaction pathway for the reaction to occur. So here's an example. So this is the reaction of forming water, and then you'll notice that you can recognize a catalyst because there will be a little element symbol. For example, platinum is a very common catalyst for reactions. And so there'll be a little symbol above the arrow, and that'll tell you that a catalyst is added. It's on the top of that arrow there because in a catalyst, it's used and then reproduced in a chemical reaction. So meaning that it's not really a reactant and it's not really a product because it's just always there in the reaction. So as I mentioned, a catalyst increases the rate of a reaction by lowering that energy hump, by lowering that activation energy. An inhibitor does the opposite. An inhibitor is a substance that decreases the rate of reaction by increasing that energy hump that you can picture in that energy diagram. All right, chemists, so that was your first introduction to rates of reaction. I hope this video was helpful. You want to start worksheet 1. Thanks so much for watching.